Alright, time for another draftphysics.com video presentation. Okay, quantum physics, Jim Al-Khalili guy. I have played this video before in the past, and I'm just better prepared to point out how this is just so wrong, and all of it's premised on just trickery and fooling people with statements about what took place and what is true that just aren't true. And yeah, it's just junk science.
Beneath the complexities of everyday life, the rules of our universe seem reassuringly simple.
All right, so why say that when you're saying they seem something entirely different? They seem insanely crazy and screwed up. So yeah, and it's not about seem, it's just what we know, right? So I mean, I could just make these arguments. You're going to throw a rock. We know the gravitational force is going to push the rock. The rock's going to hit the water. And it's going to settle on a surface that has as much pressure as it can apply. And that differential, you don't have any explanation for it. You just pretend it's some bent geodesic that's causing the effect. And you have very good reason to say, well, look, it's the same speed as light, it's the same speed as magnetism, same speed as all this other forces. Why wouldn't I think this is also a consequence of little discrete bits of energy in the universe, and somehow less of them are coming out of the earth than going into the earth, and therefore if you're in the differential, you'll get pushed in the differential. Again, they teach this subject. Leonard Susskind teaches relativity by using mock gravity, by using a physical mechanism to push objects into the center of the gravitational body. So it's fits, it's not a problem. Why pretend the physics is broken when that simple explanation is fine?
This solid bridge supports my weight. The water flowing underneath always goes downhill.
And you know the bridge is under some stress, though. If you made the bridge out of a lighter material, you'd see the stress. So you know there's energy going through the bridge into the earth. Your weight isn't inconsequential.
And when I throw this stone, it always flies through the air following a predictable path. But
yes, from a very consistent real force. And as you drop that single rock, what you create are a bunch of waves, and there's no diffraction pattern. There's no event taking place where the waves are interfering with themselves. So the single slit in water doesn't work. Yeah.
Scientists peered deep into the tiny building blocks of matter. All such certainty vanished.
So this is the nonsense part, because they didn't really delve into anything. They just made a bad model and then made excuses to say, well, we can make up anything. We can have gremlins, we can have any kind of little magical functions, because nobody can see it and prove they don't exist. So that's all it became, was gremlin science.
They found the weird world of quantum mechanics.
So there was no they, there was like 10 people. They decided what physics was going to be. And there really wasn't any hard discussion. There wasn't any hard argument. There really wasn't any... there's no debate, and then there's no moderator, and then there's no judge, and there's no jury. So it's just basically, some sort of, you could argue, a popularity contest. But it disappoints me that scientists would choose the silly answer.
Deep down inside everything we see around us, we found a universe completely unlike our own.
So it doesn't make any sense, we know it's all the way down kind of universe. And the fact is there's only one universe. That's what we have found pretty reliably. And it's made out of electrons and protons. They have the function of charge. They also have the function of momentum. And they're doing all the moving, and everything else is just about electrons and protons moving. All physical substances are just made out of electrons and protons, and it's just how your electrons and protons move decides what you do. It's the only universe there is. It's the real universe with the empty space in it and the actual things that can't be, that don't have any divisibility.
To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real.
So it really isn't true. The simple model does work. They just broke it for no good reason. Just like momentum does explain motion in our universe. You don't need 1/2 mv squared. It doesn't work. It doesn't give you right answers. If you just follow the momentum, it makes perfectly good sense. So why break it? There's no good reason. Religion, because it's not a good enough story. They want a funky story. They don't want a simple explanation for our function.
Around 100 years ago.
So he uses this more than once, this erecting of the telescope. And it's just almost juvenile, the use of it. And it's so out of place, and every time he uses it, it has nothing to do with actually looking at the universe.
Some of the world's greatest scientists began a journey down the rabbit hole into the strange and the bizarre.
So again, more talk, just talk about the world's greatest scientists declared by them each other. They basically told each other who's great. It wasn't a public election or anything. It's, it's not like they had to get elected to be, the prize winner. So it's all just sort of just, a pope said so.
They found that in the realm of the very small, things could be in two places at once.
So just absolute nonsense, I mean, so silly. You're saying, well, what do you mean two? How can the same space can't be occupied by two things? It's not even a sensible in any way statement. And they obviously don't have any evidence of it.
That their fates are dictated by chance.
So there's no such thing, okay, in the sense that there's just, there are probabilities, likelihoods of stuff, but everything's already written, so to speak. The universe is in motion, and all of the motion is by set rules. And frankly, if we could know where everything is and what everything's doing, we could perfectly predict where we're headed.
And that reality itself defies all common sense.
So just more nonsense. Defies being reasonable, yes. So if you want to believe this crap, just be unreasonable. Assume that tiny shreds of evidence and, little, there's so many ways that it's cheated, okay? I mean, I brought up the stupid carts. They sell these stupid carts to do experiments in labs. And they're made they're supposed to be low friction. Now, every time you see a low friction cart made for some other purpose, like solar energy or even carts, they make them like who can make a car that'll go the furthest on the energy in a mousetrap. Big giant wheels made out of paper, right? Light and big. And what kind of wheels are on the low friction carts? Oh, little tiny metal wheels. Okay, so the axles are spinning very fast, the wheels spinning very fast, lots of angular momentum trapped in those wheels. That's not what you want to do when you're doing a linear experiment, is trap half the energy in a bunch of rotating wheels. Now, it's a real fact. It's just a fact. That's not how you would make it if you really wanted to do a linear experiment. That's not the cart you would make. That's just a fact.
And at stake, that everything we thought we knew about the world might turn out to be completely wrong.
Yeah, so it's all just nonsense, and thought from who? I mean, we've all been raised on this wooey crap. All right, you ruined physics 100, 200 years ago, and you just keep ruining it. You just keep going further and further into silly, preposterous, nonsense explanations. Dark matter, for example, neutrinos. I mean, just all this invented nonsense. Antimatter, quantum computing.
The story of our descent into scientific madness begins with a most unlikely object. Berlin, 1890. Germany is a new country, recently unified and hungry to
Who cares?
industrialize. In this newly unified Germany, a number of new engineering companies were founded. They'd spent millions buying the European patent for Edison's new invention, the light bulb.
So all of this really doesn't have anything to do with the story. I mean, all this useless context. Obviously, the light bulb was a scientifically interesting development.
The light bulb was the epitome of modern technology, a great optimistic symbol of progress.
I'll agree that it's a symbol of progress, but I don't know about this technology part. It's electricity burning a wire.
Engineering companies quickly realized there were fortunes to be made building streetlights for the new German Empire. But what they didn't realize was that they would also unleash a scientific revolution.
No, brother. I mean, all this babble. Now, the thing the light bulb should tell you is that's the inverse square law. Right there's the inverse square law. The light flies off at the inverse square law. It's coming from a point, it spreads out in 2 dimensions, and the particles of light, the photons, get weaker and weaker by the inverse square law. Exactly the same law governing gravity. So you can sort of understand that, well, if I just reverse what the light bulb is doing, it's basically gravity. I have exactly the same capacity to say, okay, that's all I have to do. Just create a mechanism where more goes in than comes out. All right. And obviously, if the simplest way to do that is to use up some of the energy melting the center of the earth. Yeah, that's a good way to lose the energy, is to have a furnace you have to constantly feed.
Strangely enough, this humble object is responsible for the birth of the most important theory in the whole of science.
No, I mean, it's just, all this is just, who knows what was in people's heads when they did experiments, but whatever, this is just bullshit.
Quantum mechanics, a theory that I've spent my universal
Yeah, you spent your life babbling about. So, my life studying, he says. And so, yeah, with a clear bias. Instead of being a little skeptical and saying, well, what, is this all the evidence they have?
And that's because back in 1900, the light bulb presented a rather strange problem. Engineers knew that if you heated the filament with electricity, it...
Well, yeah, and why does it do that, right? I mean, it's basically is melting, degrading, breaking the filament. The filament degrades because you really are hurting it. So that's why you're getting energy out of it, is because you're doing damage to it.
Glowed. The physics that underpinned this, though, was completely unknown. But something as basic as the relationship between the temperature of the filament and the color of light it produces was still a complete mystery.
Right. So, I mean, look, Newton did rainbows a long time ago. And so he had to figure out how, this light would bounce inside of a, first it would bend going into the light, the water droplet. Then it's going to reflect internally twice or 3 times. And, he had to figure all that out. And none of that required any of this wave crap or quantum mechanic crap. Okay, he did all that with just basic geometry of bullets. Fact.
a mystery they were obviously keen to solve.
So you're saying you have atoms and you jiggle them and you get this, frequencies of light out, and you can say, well, maybe this is just about a frequency. So that part they knew in the 1900s, it was about a frequency. And you're just saying, well, how do I jiggle it faster? I mean, how small does something have to be, or what's the thing? And obviously the size of the atoms matter. Obviously, you could argue the density of the compact electrons matters. It's going to decide what color of light you can produce, because it's going to have to do with what electrons are actually doing the moving.
And with the help of the new German state, they saw how to steal a march on their competitors.
So I don't know why all of this crap is in there. I mean, I don't think the Germans monopolized the light bulb industry or something.
In 1887,
So he's going backwards now.
German government invested millions in a new technical research institute here in Berlin, the Physikalisch-Technische Reichenstadt, or PTR. Then, in 1900, they enlisted a bright, if somewhat straight-laced scientist to help work here. His name was Max Planck.
So way oversold also, okay, but smart guy, no doubt about it.
Planck took on a deceptively simple problem: why the color of the light changes as the filament gets hotter. To get a sense of the puzzle facing Planck, I'm going to ride this bicycle with an old-fashioned lamp powered by an old-fashioned dynamo.
So you can sort of understand there would be a relationship between something called speed, okay, and frequency. I mean, that's not too hard to figure out, right? That something bouncing faster or something bouncing between things further apart would create a different frequency at the same. So if you had the same speed but just had things further apart, you'd have a different frequency. So the whole idea that it's, you can make it out of particles is the point. It works. All this antics, all this antic physics.
Obviously, the faster I go, the brighter the light. The more I pedal, the more electricity the dynamo produces, the hotter the filament in the lamp, and the brighter the light. But the light the bulb makes isn't just getting brighter. It's changing color too. As I speed up, the color shifts from red to orange to yellow. Right, now I'm going to really belt it. Now the bulb's
brother. To make a simple point.
Filament is getting even hotter, but although it certainly gets brighter, the color seems to stay the same.
Right, and the argument could be made, well, yeah, and gamma rays don't fly out either, and X-rays don't fly out, and a lot of other stuff doesn't fly out. So, yeah, I guess that stuff requires you to really break the atoms, to really make a mess out of the filament.
Yellow-white. Why doesn't the light get any bluer?
So the argument's just that simple, is that you're really talking about this whole thing has to happen because you're going to move electrons, and the thing that's going to you're deciding is how fast they move, because electrons can vary their speed. So the speed at which they move is going to decide how high a frequency you can get. But the only way you can make them electron go faster is you have to put in an awful lot of energy to get them to go that fast. So it's the speed of electrons that decides what the frequency of the light's going to be. And the speed of the electrons, obviously, you have to hit them with an awful lot of radiation to get them to go that fast.
To investigate, Planck and his colleagues built this, a black body radiator. It's a special tube they could heat to a very precise temperature and a way to measure the color or frequency of the light it produced.
So you're always just heating a substance. You know, there's no such thing as heat in space. You have to heat a material. So the whole concept is kind of just always dependent on what you're heating.
Nowadays, over 100 years later, the PTR still do exactly this kind of measurement, just much more accurately.
For what purpose, one wonders.
The temperature inside here is 841 degrees centigrade. I can feel the heat coming off, and it's glowing with a lovely orangey red color.
Very exciting.
It's about the same color as my bike light when I'm cycling slowly. But I want to see something hotter still. The temperature inside here is about 2000 degrees centigrade. And it's glowing with a much brighter, whiter colored light.
Now it looks whiter in this picture. It didn't look so white in the close-up, but whatever.
To produce light of this intensity and color requires a power of about 40 kilowatts. Now, that's equivalent to...
So this is all just who cares. It really depends on how much space you're heating and all that stuff. So you could probably do it with 20 kilowatts, or you could do it with 100 kilowatts. You could use any various numbers depending on how much space you intend to heat.
About 400 mies on a bike cycling very fast, or the combined output of the entire Tour de France.
Right, so it's obviously not the combined output, because the little tiny generator on your wheel was only a tiny proportion of your total work you put into the bicycle. So that's kind of silly also.
Although the light is whiter, it's red-white. There's very little blue. Why is blue so much harder to make than red? And further up the spectrum, beyond blue.
So again, you could just answer the question by just saying, if electrons moving, doing that, you know, going out, going in, going out, going in, if that's creating a photon, if that's the frequency of the photon, you can understand that, yes, moving electrons very fast would be more difficult than moving them very slow.
The so-called ultraviolet is hardly produced at all, even when we look at things as hot as the sun. Even the sun, at a temperature of 5,500 degrees centigrade, produces mostly white visible light and makes remarkably little ultraviolet light given how hot it is. Why is this? Why is ultraviolet light so hard to make?
You could argue that the light sort of has to be made out of light. So it's almost like the light is conserved. I mean, you know, in a sense, the frequency is conserved. And so it's what's inside the atom decides what's the atom's capable of producing in terms of pressure and on electrons. So the pressure inside of an atom decides how much an electron can move.
This remarkable failure of common sense so perplexed scientists of the late 19th century that they gave it a very dramatic name. They called it...
Try killing bugs the worry-free.
Shit. Alright, should be back. The ultraviolet catastrophe.
Violet catastrophe.
So this was described different ways, like if objects could produce ultraviolet light as easily as they produce these other kinds, then we would all be incinerated by the ultraviolet light. And really the limitation isn't that it takes more energy, it's that it takes energy in a form that the universe just doesn't produce enough of, like gamma rays.
Planck took a crucial first step to solving this. He found the precise mathematical link between the color of light, its frequency, and its energy.
So its energy, the pieces that make up the light, it's all the same energy. And all you're saying is that if I change the frequency, what I'm changing is the impact rate. So I can change something. I've used this example. I could throw 3 baseballs. I could throw them in 3 seconds, or I could throw all 3 of them in the first half second. Now, the fact that all 3 of them are going to hit something in the in the half second means that that same amount of energy has to be absorbed in a much smaller amount of time, and most things won't be able to absorb it. So if you want to break glass or something, you hit it quickly, and if you could throw metal balls at a glass and they could just bounce off and bounce off. But if you throw them so they hit each other right after each other, then they'll break the glass, because the glass can't absorb the energy as quickly as you're putting it in.
But he didn't understand the connection. However, it was another weird anomaly that would really put the cat amongst the pigeons. In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one.
Yes, so this is this is another version of the photoelectric effect, in the sense that you obviously can create extra charge on surfaces by shining light on them.
By spinning this disc, they could generate huge voltages that caused sparks to jump across the gap between the 2 metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity.
Well, it all seems like it should be connected, in the sense that it's all momentum, it's all energy of some kind. And obviously, it just seems kind of obvious that, yes, adding more energy would make something happen.
To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version.
I think these are all separate experiments. I don't think the other guys were trying to demonstrate that effect when they were just looking for this one based on metals.
Of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the 2 gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected. Now I'll try this special blue light, rich in ultraviolet. Immediately, the gold leaves collapse.
Wasn't exactly immediate, but whatever. Right. And so again, you're basically saying, okay, there's something about light and frequency. Now, you already knew that because you already discovered X-rays. And so you already knew that light has really different properties at these different frequencies. And so that part should be no big surprise. So, okay, continuing. I mean, the reason why the higher frequency has more energy is just because of this tipping point argument. The faster, if you move something, you hit something, and especially for electrons, the argument would be is they're stuck in tension. You hit the electron, you're moving it out of its tension, it's going to be pushed back again. So it's not only going to decelerate after you hit it, it's going to go back. And the whole point would be is that obviously hitting it before it slows down means you can get more energy into it, and means it'll reach a higher peak velocity. So the sooner you can hit it with your pieces of energy, so if you only have 3 baseballs to throw, and you throw them quickly, then you'll get a higher peak velocity out of the thing you're hitting with the baseballs. It's that simple. And they've turned it into all this woo. I mean, it's really not more energy. There's not more. His analogies are going to be terrible, so I might as well wait till he gets to the terrible analogy to complain. But it's all wrong. This is just a tipping point argument. You have to add energy when something's still moving in the direction you want to move it. And if you want it to get the peak velocity, you have to add the energy before it slows down.
Light.
Let's understand the light's moving the speed of light. So anything it's going to push, even an electron, is going to go a lot slower than the speed of light. So you're hitting it with an amount of energy that can go from 0 to 10, or it can make it go from 10 to 20, or it can make it go from 20 to 40, or you can go higher because the speed of light is so much faster than the velocities you're moving the electron. So each clump of energy is a full clump, and how fast you're already going doesn't make any difference. Until it gets up to half the speed of light or so.
It can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why?
And so the simple answer to that is yes, because the electrons have a higher velocity. You can't give them a high velocity if they keep slowing down before you hit them again. So if they keep going back, that's even worse, right? If the pendulum's swinging back this way and you try to hit it, you're not going to add velocity.
Is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. The ultraviolet catastrophe and the photoelectric effect were big problems for physicists, because neither could be understood using the best science of the time. The science that said quite unequivocally that light was a wave.
Right, and it should be equivocal. It shouldn't have been unequivocal, because there are so many circumstances where ray of light works. There's so many, and even, these stupid examples they use like shadows and the rest of it. Well, of course you would think the surface is not some kind of smooth thing. And so, of course, photons of light could be bent by surfaces. Clumps of light.
All around us, we see light behave.
Say this is the silly part, right? Because Newton made almost the opposite argument. He made the argument that, it doesn't spread out very much. I mean, the fact is it doesn't spread out very much. I mean, considering how much waves fill the gap. So if it really was waves, it would be your shadow would be a lot blurrier. It's only a little bit blurry, indicating it is particles.
Behaving in a perfectly common sense, wavy way. Look at the shadow of my hand. It's fuzzy around the edges.
Yeah, just the edges. And if the wave theory was right, it would be, it would spread out even more. There'd be even a lot more fuzz. Waves would just keep, going into the surface, and make a mess out of your shadow.
We understand.
Your shadow would disappear so much quicker.
And this as the light hitting the sides of my hand and bending and...
Right, and the simple argument is the light is hitting the surface of your hand, and it's hitting electrons, and the photons are, and it's being scattered in all directions, and where enough of it hits the same place, you put the photons back together.
Smearing out slightly, just like water waves around an obstruction.
So it isn't just like water waves. It's a lot different than water waves. Water waves would make a lot bigger mess.
Perfectly common sense, wave-like behavior.
So you can't make very good shadows with sound or water.
And here's something else, something rather beautiful.
So this is the part where you say, this is Newton's corpuscle theory explained rainbows in the 1600s, okay? I mean, it's amazing. So he knew about all this, thin film kind of stuff, and a particle theory worked just fine.
Look at these soap bubbles. Shine a light on them, and gorgeous coloured patterns emerge from nowhere. And this was easily explained if you accept that light was a wave.
So it's no harder to explain if you make it into particles, because it's really just about distances and frequencies. And that's it.
Reflecting off the outer and inner layers of the thin soap film and breaking up into the colours of the rainbow. Rather like ripples on the surface of water, light was simply ripples of energy spreading through space. And this was as firmly
So again, and the similarities again disappeared. The single slit in light produces a pattern. The single slit in wave water doesn't.
accepted as the fact that the Earth was round. But although this wave theory worked perfectly well for shadows and bubbles, when it came to the
So it doesn't work perfectly, that's for sure, and it doesn't even work well. So
ultraviolet catastrophe and the photoelectric effect, the wheels started coming off. The problem.
So all this antics, he gets in a wave tank when we know this is about a frequency, and even if with using waves, it's about a frequency. It's not about how much volume of water it is. So it's such a poor analogy because it doesn't prove that a wave theory can't explain. It could, because it's just a frequency. So again, if the real argument is the tipping point, waves can tip things. So it really doesn't solve the wave issue. So again, they're so bad at this. These analogies are just terrible.
Was this? How could light do this? To truly grasp how absurd this phenomenon was, it might be useful to consider how waves in water behave.
So there really isn't anything absurd about it.
This is the wave tank at the RNLI's headquarters in Dorset. It's used to train lifeboat teams to deal with a range of different kinds of water waves. First, small waves, just 30 centimeters high. These waves don't have much energy, hardly enough energy to knock this top pan off the other.
That's some experiment, ain't it? Yeah, no, I don't think that's much of an experiment. Oh, that's scientific? I don't think so.
But when the waves grow to over 1.5 meters, it's a very different proposition. And they're really throwing me about. There's no way I can keep this pan balanced on the top.
I don't even understand what he was trying to do. It's such a silly experiment.
It's clear what water waves are telling us. Bigger, more intense waves have more power.
So again, just kind of silly to say that, radio wave that's a mile long, or, some kind of nonsense that it has more power, because it's a big wave. No.
They easily knock me and the cans around. So if light was a wave, more intensity should knock out more electrons.
So again, intensity wouldn't be the number of water molecules moving, a height. So those are two different things, volume and amplitude. So he was increasing both the volume of water and the amplitude of the water.
But that's not what happened. Remember, no matter how intense the red light was, it still didn't budge electrons from the metal. But weirdly...
So, and by the simple explanation that it's delivering the energy too slowly, at too slow an interval, all right, to increase the velocity of an electron to a high enough velocity. So it gets hit, say, 3 times, but it's getting hit 3 times with enough time in between, so the electron has lost velocity. So it never achieves its highest velocity.
Weak ultraviolet worked within seconds. So thinking of light as a wave just wasn't adding up.
This is sort of like the Feynman argument. So Feynman makes the argument that it's not a wave. And he makes the argument, but I think it's just not a really great argument to make, because yes, all of our detectors are clump detectors. So because our detectors are clump detectors, we're saying it can't be a wave. That's sort of cheating. It's not a wave because there's no evidence that photons are in any way connected to each other. They can't wave. They're independent little pieces of shit, okay? And they can fly. I mean, the laser beam should end the argument. There's nothing waving there. I mean, you can't get more obviously a stream, a ray of light. It's certainly not a wave of light.
To resolve this, someone needed to think the unthinkable. And in 1905, someone did. You may well have heard of him. His name was Albert Einstein.
And it's surprising that he didn't take it any further. You know, that, you know, he had, you know, 2 years before he died, he said, you know, I spent 50 years studying photons and I haven't improved my understanding. You know, that's just kind of surprising.
Sternbach Observatory in Berlin.
So again, this has absolutely nothing to do with anything. So in 1915, he did a lecture from this observatory. He wrote the paper on the photoelectric effect 10 years earlier. So this has nothing to do with the story at all.
Berlin. Perched on top is a strange, huge iron and steel construction. But it's not a gun. It's actually...
They just wanted an excuse to erect the telescope.
A telescope.
That's all they wanted to do. They wanted to do this.
In 1896, the telescope was one of the largest of its kind in the world and made the observatory the go-to place to engage and establish...
in funny jokes.
...the public in new science. Albert Einstein gave a very famous public lecture here on his theory of relativity.
In 1915.
Which is, of course, what he's most famous for. But it's not the work that won him the Nobel Prize. In 1905, he'd also come up with a new theory to explain the photoelectric...
So what? So what did they do? What is this theater, right? So he's talking about light and photons and the photoelectric effect, and they're showing a telescope. I mean, yeah, this is it's just, you're saying, and you're a physicist and you can't figure out how there's a continuity problem? Shit.
Effect. And what he suggested was revolutionary and even heretical.
Well, clearly, yes. It's that's the key word. It is just a heresy to disagree with this bullshit Woolacole physics.
He argued that we have to forget all about the idea that light is a wave and think of it instead as a stream of tiny bullet-like particles.
So he didn't say this exactly right, because he's still saying the photon is one of the bullets rather than the photon is a sequence of bullets. So that's the part that's unclear. I couldn't figure out what he is exactly saying in the paper, so because it just wasn't clear enough. So, I mean, if the photon he's arguing, is the composite byproduct of a series of bullets hitting at a frequency, then we agree. But I'm not sure that's what Einstein was saying.
The term he used to describe a particle of light was a quantum.
So I would use the term that is a piece of light. It's a component of light. It isn't a photon. Quanta makes photons. And do it again. They're doing it again. They're still playing with their telescope. Jeez, go blind that way.
Einstein, a quantum was a tiny lump of energy. And although in 1905 the word wasn't new, the idea that light could be a quantum seemed crazy. And yet, following Einstein's heretical line of...
So again, this whole idea is that all you're saying is that we already know the universe is already full of this stuff. And it comes at all these different frequencies. Well, what if it's not at a frequency? You know, what if it's just chaotic? How do we detect it then? Oh yeah, maybe we drop something on Earth and we'll detect it.
Thought to its logical conclusion solved all the problems with light at a single stroke.
So clump theory works in terms of, but again, it's the way they're saying it just doesn't make any sense, because they're going to imply that somehow the quantum gets heavier. You know, that somehow ultraviolet quanta is heavier. It's not any heavier. It just happens quicker. It doesn't move faster, but it happens in a smaller amount of time. It delivers its hits in a smaller amount of time.
I'll try to explain how this helps using a rough analogy. Of course, like all analogies, it's far from perfect, but hopefully it'll...
It's not even close. This is so far from... Again, the tipping point thing is a close analogy. And the even closer one would be one that just points out that the quicker you add energy before something can slow down, the higher the peak velocity you can give it.
Give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect.
So they never really get to this idea that the reason why what photons are actually doing is hitting electrons, and what they're doing is giving them momentum, and that they have to have a certain momentum to leave the surface, or a certain momentum to transfer from one atom to another to create electricity. So electricity is the electron having enough energy to jump to another atom, and then the other photoelectric effect is where you actually give the electron enough energy to leave the surface. And it's just about transferring the momentum. And you can more efficiently transfer momentum with high frequency light than you can with low frequency light.
In this analogy, these red balls represent Einstein's light quanta. And those cans over there are the electricity held in the metal.
So nowhere in this analogy is frequency exist. So that's why it's just so poor as an analogy. Instead, all he's doing is saying, look, red ones are light and the blue ones are going to be heavy, golf balls. And that doesn't explain it at all.
Now, in the original experiment, they made electricity flow from the surface of the metal by shining light. Critics are falling in love.
Okay, so we don't need to flow from the surface. We can also just make it flow through the surface. So the photoelectric effect has two effects: launching electrons off a surface, and also just making electrons move in the surface. So there's two velocities. One velocity that creates electricity, and a higher velocity that creates free electrons. All right. So it's probably enough for now. Let's see. Yeah, I'll get rid of the commercial and come back to this later. Alright, should be back and such. So this is a really bad analogy. And the really good analogy would be just recognizing that if you had a certain amount of energy to deliver, 200 watts, and you could deliver it in 1 second versus 4 seconds or 10 seconds, that the energy would have more potency just about with everything, okay, you interact with. So it wouldn't matter. I mean, all of the physical things we interact with, kind of obey this tendency to be more excited the faster the energy is delivered. And so you would think that, yes, the same holds true for electrons. This is just, I hate to say it, but I mean, these are physicists. They should have figured this out. I mean, it's just really lame.
In my analogy, I'm going to try and knock those tin cans over using these red balls.
Right, so nowhere in Einstein's statement is the idea that, okay, these have more momentum or these have more mass. It's just about the fact that the smaller frequency means they're closer together. They're delivered in shorter periods of time. Fast punches do more potential knock-it-over damage than slow punches. Some more silly theater. Throws like a girl.
Absolutely.
It misses a lot. He's throwing him, and you see right there, he missed every can.
No effect.
Hilarious.
That's just like red light. According to Einstein, each particle of red light carries very little energy.
So again, it's not, Einstein's paper doesn't say that much, so you can't really say that. But the idea is yes, if you spread the energy out over a longer period of time, it's going to be less effective. So it's about how effective energy is and how you're delivering it. Just like if you push on a big surface versus pushing on a little tiny. If you put all the energy in one small spot, it seems like more energy, but it isn't.
Because
I mean, like I said, physicists shouldn't be fooled by things this obvious.
red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate.
Again, the dislodging part, the reason why the volume doesn't help you any is because a photon is spread over a pretty large area. It's not about hitting one little tiny spot. It's about adding energy to an electron. So you're basically hitting one spot on a surface, the electrons all move, and you're hitting again behind the electron, and it moves a little faster. So it's that's why volume isn't going to help.
Just like the red balls. Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans.
Right, so this is, oh, okay, we all couldn't figure out what's going to happen.
With these.
So you could just skip this whole analogy showing thing because what? Who has some doubt about the outcome?
They're like the ultraviolet lights in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency.
So again, missing the whole point of why frequency matters, and that frequency isn't more energy, it's more energy per unit of time.
Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf. So Einstein's idea that light is made up of tiny particles or quanta is a...
So again, that would be the key phrase, right? Made up of. So yes, if that's what Einstein was saying, then I agree with Einstein. And Einstein the people should have realized it's a perfectly rational way to understand a photon is a sequence of events, quanta at a sequence. Yeah. but nobody did that because they never had a conversation about how many quanta it would take to make a photon. None of that conversation ever took place.
A wonderful explanation of the photoelectric effect. I remember when I first learnt about this, being blown away by its sheer elegance. And
So again, what's elegant about it? It's just basically telling you, oh, the blue things have more energy. I mean, that's not saying anything.
simplicity. But what's more, Einstein's...
I mean, there's no mechanism involved, and again, they're always missing the mechanism, the cause for the effect. The real cause of the effect is the advantage you have by increasing the frequency. Not that it's more energy, it's just more advantageous for pushing electrons.
nifty idea also helped solve Planck's mystery of the light bulb. There was more red than ultraviolet because ultraviolet quanta took so much more energy to make.
So there's no evidence that it takes more energy, quote unquote. It's that it takes a circumstance that doesn't exist very often. So like X-rays and the rest of that stuff, the only way to produce it is to put matter in some sort of special condition where electrons are very tightly packed and can move short distances very rapidly. And that's not the common condition.
About 100 times more energy. No wonder there are so few of them.
So no evidence that it takes more energy. So, they don't have that experiment. But anyway, all right. So we'll leave off here and do a part 2 and 3 and whatever it takes. 20 minutes. Yeah, that's about how it works. So it'll probably be 3. But anyway, so it really gets into some loop-de-doo. Anyway, so till next time and such and so forth and whatnot. It's just sad that I just can't believe everyone can be convinced by this silly nonsense of wooey wavicles, stuff not being, the whole idea of having a mechanical universe where, the rules are really simple, the pieces are really simple, and it just runs. But apparently that's too offensive to your religious dispositions.